Okay, so it's my pleasure to introduce our next speaker. She's Mercedes Perez Millan from Buenos Aires, and you can see her title.
Okay, so it's yes, it's joint work with Alicia. Alicia Loli, also from the University of Buenos Aires, and Richter from the Universidad Federal de Itaichuba. So I will talk about enzymatic networks, just to tell you what they are. I will show you the equations that we work with. I will say what multistationarity is, and I will focus on the role of intermediates. I will tell you in a second what that is. I will talk about messy linearly binomial systems, and if I have time, I will mention a lifting of multistationarity results. So, so enzymatic reactions. Let me see, like this. So inside the cell, there are proteins interacting, and one type of reactions is the enzymatic reaction, where there's one protein that is modified and the other one that is not modified, but helps the other one get modified. For instance, here we have this protein S as substrate, the enzyme E, so they bind, and then when they unbind, S is modified. So the scheme is up here, so you have a 0 that gets modified and transforms into S1 with the aid of E. So the equations are sorry, the actual graph that we write, the graph of reactions is this one. So E plus 0 binds to S0. So you have E, you have a 0, they bind into this intermediate species, and then they unbind, and you get S1, E plus S1. And there's usually the reverse reaction, let's say, where there's another enzyme F that transforms S1 into S0. So we number the species and we look at the concentration of the species, and so we have from X1 up to X6, and these concentrations vary in time, so we have the equations that describe those variations. This is an autonomous system of ordinary differential equations. And what I want you to look at is that they are polynomial in the species concentrations. These derivatives have linear relations among them. So you have the conservation laws that I show you here. And in these biological networks, they usually have a biological meaning. For instance, this last equation, X4 plus X6 equal CF, means that here F is either free, the enzyme F is either free or bound to the substrate S1. So the total amount remains constant, and that this is this CF. So we can write this linear system as a matrix time the vector of species concentrations equal to a vector of constants. And if we write it down equal to 0, we get a subspace. I write it down here. And this subspace is called the stoichiometric subspace. So multistationarity means that, first of all, we consider the system with conservation laws. We call these derivatives F. So these are the polynomials in the X1, Xs that depend on the constants kappa, the reaction constants kappa. And we also write down the conservation laws. And given positive reaction constants kappa, X star, a non-negative X star, is a steady state if f of X star equals 0. So in other words, given that you may know what I'm saying, X star belongs to the variety determined by these polynomials F. And if there exist positive reactions constants kappa and conservation constant C with 2 or more steady states such that satisfy the conservation laws, we say that the system exhibits multistationarity. So you have here the variety of steady states, this green curve down here, and you have, well, the stoichiometric subspace down here, and then the these varieties determined by the conservation constants. And if you have at least one of these varieties, which are called stoichiometric compatibility classes, where you have two or more steady states, then the system exhibits multistationarity. Otherwise, it says that it is said that the system is monostationary. So I said that we will focus on intermediates. So I will not be very technical about what intermediates are, but I'll show them on an example. So consider, for instance, this two-side cycle, where S0 gets transformed into S1 with the aid of E, and then S1 gets transformed into S2 with the aid of E, and then F goes back. Then the intermediate species or complexes are these species where both the enzyme and the substrate are bound. Okay, so ES0, ES1, FS2, and FS1. And the question is, which intermediate complexes are necessary to gain multistationarity? So why gain? Well, we prove that this system and many other frequent systems without any intermediates is or are monostationary. So intermediate complexes are important for gaining multistationarity. And we prove this by visually inspecting some associated digraphs. So where do these digraphs come from? And they come from a previous work with Alicia, and they're called MESI systems. MESI stands for modifications of type enzyme substrate or swap with intermediates. They also come from MESI, of course. And in these systems, they are special because there's a partition of the set of species, and there are only certain reactions that can occur. And this seems quite restrictive, but this partition is intuitive because you have the substrates in one set, the enzymes in another set. So it's easy to find these partitions. It's frequent to find them. They're related to the conservation laws, and the reactions are, for instance, enzymatic reactions. So let me show you a more interesting example. So this is the 3-layer cascade. So here, up here we have the cycle we saw before, and then S1 goes and acts as an enzyme and transforms P0 into P1, P1 into P2. There's another enzyme that goes back, and then P2 acts as an enzyme transforming R0 into R1 and then into R2. And in this case, the same enzyme goes back. And for instance, this cascade represents the ERK signaling pathway, which is quite important in cell functions, because this ERK protein here goes and activates many transcription factors that are crucial for the cell reproduction. So it's a very important pathway in the cell. So let's go back to math, and we show that many systems like this one are monostationary by inspecting, as I said before, some graphs. So let G be a MESI system and some hypotheses that I will show you down here with this graph, then the system is monostationary. So first of all, we ask for the network to have no intermediate species. Well, that's easy to check. And then we build this multi-digraph MG2 this way. Let me just show you one example. So for instance, when you consider this reaction where S0 plus E becomes S1 plus E, we say that S0 gets transformed into S1 with the aid of E. So E comes here together with the reaction constant tau in this case, tau1 times x9, which is the concentration of E. But we also say, and this is quite artificial, but that E becomes E with the aid of S0, and here we have this loop. E becomes E with the aid of x1, which is the concentration of 0, times the reaction constant tau1. And like this, we build all these arrows, and we have to look if there are parallel edges between different nodes. And in this case, we do not have that. Here we have several parallel edges, but they start at F2 and end at F2, so it's the same node. And here these have different directions, so we are okay. There are no parallel edges between different nodes. And as I said before, these loops are quite artificial, so we just take them away and we build another digraph, which is G20, which is the same graph without these loops. And we have to check now if any two nodes that are connected by unique simple paths. And that is the case. If you have any two nodes that are connected, they are connected by simple paths. And there's only one simple path connecting them. Simple paths means that you do not go through the same node twice. And finally, we have this other digraph GE, which is built like this. So as I said before, this partition of the species is quite natural in this biological context. So we have, for instance, the set of S0, S1, which are transformed one into another, then P0, P1, P2, R0, R1, R2, and then each enzyme in a separate set. So as S0 becomes S1 with the aid of E, we have an arrow that goes from the set of E S4 to S1, which is the set of the S, and so on. So for instance, S1 gets transformed into S0 with the aid of F1, so we have this arrow here. And we have to check if there are directed cycles in this graph, and this is not the case because we have a cycle here, but it's not directed. So we're fine, and this three-layer cascade then is monostationary without any intermediates. And if we also check G20, and we see that the underlying undirected graph is a forest, which is the case because each connected component is a tree, then we can say, and here we say it, that G and any canonical extension are linearly binomial networks. So canonical extension means that you can add intermediates in a proper way, and it still is linearly binomial. And linearly binomial, well, linearly binomial systems, the idea is that they are such that the polynomial system of equations f of x equals 0 is equivalent via linear operations to a binomial system. So for those who are not sure, but a binomial is a polynomial with two terms. And if you have a system of binomial equations, then you have structure, and you can say many things about the system. If you happen to have at least one trinomial, then you have anything, so you cannot say anything. But in this case, if you can make it binomial, which is the case here, you have structure, and that is great. So formally, a linear binomial system implies a matrix M that is well defined for all positive rate constants, that has positive determinant, that you can get the binomials multiplying the linearly independent set of F's times this matrix. And then you consider the augmented system where you put these binomials of this shape, monomial minus constant times monomial, and then you complete the equations, and then you have a square system with the conservation laws. So I was talking about intermediates. Now I'm talking about binomial system. Well, let's go back to intermediates. So which intermediates are necessary for multistationarity? This question has already been addressed by another work by Sadeghi, Manesh, and Feliu, and they coined the expression circuits of multistationarity to name the minimal sets of intermediate complexes with which the system has the capacity for multistationarity. And for linearly binomial networks, we implemented in Maple their criterion, but with an equivalent formulation, with a critical function that we had already defined in a previous work with Alicia and Xu and Xiaoshan Tang. And it's also based on degree theory that from this other work from these 4 authors. And we do this to obtain the minimal subsets of intermediates that guarantee multistationarity. So let me show you, first of all, which is this function, and then an example. So we consider this critical function, which is the determinant of the Jacobian of the equations H here. Let me go back, so scrolling is slower. So this H, so we have the binomials and the linear relations. So we consider the determinant of the Jacobian of these equations, but we do something else. We solve for the constants A, or the parameters A, in terms of the X. So if we equal this to 0, we can say that A is X to the gamma divided by X to the delta. And this is what we write here. And if the system is linearly binomial, then we have already proved in the previous work that it is a Laurent monomial times B of X, with B a homogeneous polynomial only on the X variables, no constants there, no rate constants there, of degree S minus the dimension of the stoichiometric subspace, and its monomials have exponents in 0, 1. And we have a result in that work where we say that multistationarity is, you have it if and only if this polynomial has a coefficient with a certain sign, which is -1 to the dimension of the stoichiometric subspace plus 1. So we just have to inspect the polynomial and check if it has one term with that sign, and that's enough. And when you get X star such that you evaluate that polynomial in X star and it has this multistationarity sign, then you can build a witness to multistationarity, although it's quite technical, but you can. And for instance, in this example, this is the 2-layer cascade. We analyze this critical function, which is this Laurent monomial times this very nice polynomial. And in this case, the multistationarity sign is minus. So we look at the negative terms and we inspect the intermediate species here. So in this case, how we order the species such that the intermediates are x2 and x8, and we build this set, x2, x8. Then here, x8, this set, x2, x8 is already here, 4, 8 here, 4, 6 here. So we consider the minimal sets with respect to the inclusion, in this case, x8 and then x4, x6. And these sets determine the circuits of multistationarity. This means if I only add the intermediate down here, I gain multistationarity. And if I add the intermediates over here in the middle and here in the middle both, I gain multistationarity, but just one of them is not enough. And we also computed the circuits of multistationarity for the 3-layer cascade and for the following version of the 3-layer cascade with the retroactivity where R2 comes back and somehow inactivates S1. And note that the number of variables is greater than 20 and the number of parameters is greater than 35. So we deal with many numbers, but Maple is very good for this. And while doing this, we got inspired and got a theoretical result for a certain network. In this case, this network is, so we have cycles like those that we have already seen. So E transforms S0 into S1, S1 into S2, and so on. but then F removes several. For instance, if this is phosphorylation, then what you're adding is a phosphate group. So E adds one phosphate group, then two, and so on. And then F removes several phosphate groups and goes back. So we proved that the canonical circuits of multistationarity of this network are, you can add an intermediate here, and you gain multistationarity, or here, and you gain, or here. But if you start adding here, then you do not gain multistationarity. And then if you go back, almost the same. So here, 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 but here you don't gain anything. And well, finally, and I'm fine with time, we also have a result for regions for lifting multistationarity. So what does it say? So you add one intermediate and you gain multistationarity. And then if you have more, what happens? Well, you keep multistationarity. So we have this result where we say that if you have parameters for the smaller network where you have M non-degenerate positive steady states, you can go back. So you can go to the bigger network and have not just one choice for parameters to gain multistationarity, but an open set of parameters where you also have there in the bigger network M non-degenerate positive steady states. It's based on a previous work by Feliu and Youth, but what we add here is an open set. So I leave you here with some references, and thanks for your attention, for organizing this session, and for the invitation.
Thank you, Mercedes. In fact, I would like to contradict you. It's not that Maple is bad, but our method avoids the 35 parameters. So we are clever enough to make the computation feasible.
Yeah.
We found a combinatorial way to avoid so many variables.
So many variables, yeah.
This is one of the main things that we did.
Yes, but we also found the circles of multistationarity of this network, which are not, yeah. It's not nice to write down, but yeah.
So maybe it was not so clear because there were many definitions, but we are trying to understand how many positive roots we can find of the system. If there is only one, or there could be more than one. This is the difference between monostationarity and multistationarity. And the systems come from these applications in biology. This is why we have all this terminology. And using some math, we can give answers for big biological networks. But we have many, we have to introduce many definitions for this. So maybe we can stop the recording, and then we have